Hello, my name is Miriam Lopez. I am a student at the University of Texas of the Permian Basin, and I was required to do a research paper and a research presentation on Archimedes and the area of a circle for the course Math 6300, which is the history of mathematics. So we will go into some of his history. And over the proof on how he found the area of a circle. So Archimedes was born in Syracuse, Sicily, which is in Italy, on 287 BCE. So Syracuse is right here. I have a red location point on there. He was educated in Alexandria in Egypt, and a lot of mathematicians were educated there, which is pretty interesting. And he lived most of his life in Syracuse. So he was educated in Alexandria, but most of his life he was in Syracuse. He was a famous mathematician, inventor, physicist, astronomer, engineer, and philosopher in ancient Greece. He's one of the most famous and greatest mathematicians known. A little bit more about his history. It is known that he was a good friend of King Hiram II, and it is said that he screamed Eureka as he was taking a bath. So basically the story goes, it says that the king told Archimedes to figure out if the crown that he had gotten made was actual gold or if it was another metal. So Archimedes was the type of person that when he had a problem, he would focus and he would do everything he could to solve this problem. So he was very determined. So it is said that as he was getting inside of his tub, he saw that when he got inside, some water fell. So he got the idea that if he could that when he would place the crown inside of the tub or inside water, that same amount of water of the crown's weight was going to fall out. So when he discovered this idea, when he discovered this principle, the principle of buoyancy, basically, he got so excited that he ran out, and they say he ran out naked, and he ran out through the town screaming Eureka, Eureka, because he had this great idea, this discovery. This is also known as Archimedes' principle. So he was quite a character, if we put it that way. He also helped fight the Romans during the Roman conquest in Sicily with his inventions. Most of his inventions were used during the Roman conquest. Like I said earlier, he would focus hard. So unfortunately, he died during this Roman conquest because he was so engaged on a math problem. He was trying to solve a math problem. He was so engaged that when soldiers came to get him, he told the soldiers to go away. And so one of the soldiers got enraged. He got so angry that this guy was telling them to go away. Like he didn't even know the Romans had invaded Syracuse. So since he didn't know, he was over here trying to solve this problem, the Roman soldiers came to get him, and he pretty much said, "Don't bother me, I'm working on this math problem." So one of the soldiers got angry, and the soldier killed him. And it is said that their leader really admired Archimedes. So when he heard that he had died, he ordered them to bury him with honors. So a little bit on his inventions. His inventions were mostly used during this Roman conquest. He had several inventions actually. So some of these are, for example, he created grappling devices to grab and lift the front of warships and sink them. So here's a picture of that where he's grabbing the front of this warship and sinking it. He also created a mirror system that reflected the rays of the sun onto the invaders' boats to set them on fire. So here's a picture illustrating that as well. And he also developed lever and pulley devices that helped him maneuver and drop large weights on Roman ships. So this allowed him to sink ships by dropping large weights on them. More on his inventions. He invented catapulting devices that enabled him to send masses of stones over city walls to the attackers on the other side. He also created a water lifting device called the hydraulic screw. And this hydraulic screw, and let me move this real quick. This is a hydraulic screw, or a picture of it. And it is used to lift water from lower levels to higher levels. And it is said that this device is still used in developing countries. So it is still used today. One of his famous quotes was, "Give me a lever and a place to stand, and I'll move the world." So here's a little sketch on that quote, which I thought was pretty neat. Okay, so the area of a circle. He proved that the area of a circle was equal. So the area of a circle was equal to the area of a triangle, with the circumference of said circle as the base. So we have the circumference as the base, and the radius as the height of the triangle. Radius. So this concept is said to be found in two different treatises that survived. One was a measurement of a circle, and the other one was on the sphere and cylinder treatise. There is a total of 9 that survived, 9 treatises that survived. So we do have some of his work, which is pretty neat. So he found the area of a circle by using the method of exhaustion. So this is based upon the axiom that a given quantity can be made smaller than another given quantity by successively halving it a finite number of times. So, for example, you can take a pentagon and inscribe it inside of the circle, and you can take or circumscribe it, and then you halve it. So you make a polygon that has sides smaller than a pentagon an infinite number of times until you get the smallest, as close as you can to a circle. So that's the method he used, the method of exhaustion. So we're going to start with the proof. So we're going to say A is the area of a circle, T is the area of a triangle, and P is the area of the inscribed polygon. He knew that there were 3 relations possible. Either A equals T, A is greater than T, or A is less than T. We can show this by analyzing each of these cases, each of these 3 cases. So we're going to start. So he knew one of these was true. So we're going to start with A is greater than T. So suppose A is greater than T. So if A is greater than T, A minus T, since A is greater, A is bigger than T, A minus T is a positive value. So we know that if we inscribe a polygon inside of a circle, the area of the circle is obviously going to be bigger than the area of the polygon. So we can say A is greater than P. So A minus P is less than A minus T. So when we solve for T, we basically subtract A from both sides, and we are left with T less than P. We also know the perimeter of a polygon, we're going to call it Q, is less than the circumference. So the perimeter of this polygon is going to obviously be less than the circumference of the circle. And the apothem B, which is from the center of the circle to the outside of the polygon, to the side of the polygon, that's the apothem, and we're going to call that B. So B is less than R because R goes all the way to the circle. So R is obviously going to be bigger. So we can say R is greater than B. We can also say the area of a polygon, which is basically 1/2 times the base times height, is 1/2 B times Q. This is less than the area of a triangle because we're trying to find if it's equal to the triangle, which is 1/2 R times C, because R is the height, C is the base. So we can say that T is greater than P, which is a contradiction because earlier we found that T was less than P. So it can't be both. It has to be one. So since this is a contradiction, we can say that case 1, A is greater than T, is false. So we go on to case 2. So case 2, we say A is less than T. So if A is less than T, T minus A is equal to the excess area of the triangle over the circle. The area of the circumscribed polygon, we will call it S. So we can say S minus A is less than T minus A. So again, we solve for T by adding A to both sides, and we get T is greater than S. Again, we have the apothem as B, and this time B is equal to R because the apothem and R are equal. They're going to the outside of the circle, which is the same as the apothem in this case for a circumscribed triangle. And Q is equal to C. Remember, Q was a perimeter of the polygon. So we can say S is greater than T, which is a contradiction. Again, earlier we said T was greater than S, that T was bigger. And now we're saying T is smaller than S. So that's a contradiction. So obviously case 2 is not true. It is false. So A is not less than T. So since A is not less than T and A is not greater than T, we only have one more case, which is A is equal to T. So if A is equal to T, A is equal to T has to be true because it has to be one of those 3 cases, and we already proved the other 2 are false. So A has to be equal to T. So again, A is the area of the circle is equal to T, the area of a triangle. So we know, let's look at what we know. We know the area of a triangle is 1/2 times the base times the height. The circumference of a circle is 2 pi r. Okay, so T is equal, the area of a triangle is 1/2 r times C in terms of R and C. So we can say, since we know C is 2 pi r, we can say T is equal to 1/2 r times 2 pi r. Which means if you look at this, 1/2 times 2 is 1, so it cancels out basically. So now we have r times pi times r, which is pi r squared, which is what is now known as the formula for the area of a circle. So since A is equal to T, like we said before, and T is equal to pi r squared, then A is also pi r squared. So that is the proof. These are the resources that I used. This proof was basically found in this, it was a scholarly project actually, an article, and which is the 3rd resource on this page. And the author was, I think her first name was Patricia. Her last name's not. I'm not sure if I'm saying that right. But most of this proof was found on her publication, and I found it to be pretty interesting and understandable. I hope you enjoyed this, and thank you for watching.